Hello everyone, and welcome to the MATLAB and Simulink robotics arena. My name's Sebastian, and this is the first of 3 videos on walking robots. In this first part, we'll be talking about modeling and simulation of walking robots. In this video, we'll start with an introduction to the robot walker system, and specifically, we'll be digging into modeling the mechanics of the walking robot. This means building the three-dimensional model, any actuation we need to do, as well as the contact between the foot and the ground. Let's start with the introduction. So this will be our robot walker system you see on the screen. It's a simplified brick body with 2 legs. And the goal for this series of videos is to control the individual joints of the robot's legs. And you see that there are 3 joints per leg in this case. There's a hip, a knee, and an ankle. And what we want to do with these joints is to have the robot move in a straight line without any, excessively aggressive motions or unrealistic motions, and most importantly, without falling down. The way we'll tackle this problem is through simulation. Here you'll see a Simulink model of a walking robot, and this was created with Simscape Multibody, which is a 3-dimensional rigid body simulation tool. If I run this model, you'll see an animation coming up of our walking robot performing a simple trajectory as it's moving forward. So by the end of this video, we will see how this model was created, including things like the articulations, the motion of the legs, and the contact that makes this walking simulation possible. So let's talk a little bit about why simulation is important. The first thing is that you get to design without building, and this means a couple of things. First of all, is that you get to iterate on the physical robot design without actually having, to make a prototype of the robot. This can be expensive, this can take a lot of time. So having a simplified model of a robot beforehand, where you can quickly change things like the lengths, can be very useful. And of course, this ties into the second point, which is to check the feasibility of your design. In other words, once you've built a robot that is walking around in simulation, does this make sense given the specifications that you already have? Does it meet the weight requirements? Is it fast enough? Is the required power of the actuators reasonable? And finally, you get to verify the preliminary algorithms. Having a simulation model, not only lets you test the mechanical portion that you've built of a robot, but it also lets you prototype your control algorithms. Again, without having to necessarily build a robot beforehand and without having to implement these algorithms on hardware. The next part is perhaps an even more motivating part of simulation, which is design without breaking. So, it's great that simulation can help speed up the design process, without having to build things. But in addition, there's a lot of big safety components. First of all, you're able to run repeated tests. You can set up a simulation to automatically run through a lot of different cases, and you can do this without stressing the parts of your robot. In addition, you can intentionally recreate unsafe scenarios. For example, if you're trying to avoid certain issues that might come up, you can test them in simulation and see whether your algorithms or your design is safe enough to avoid those. And it's not only, the unsafe scenarios that are going to be there, but simulation also lets you discover new issues in a safe environment. You can imagine that in any engineering project, you probably will discover new problems. Being able to do this in simulation, where the worst thing that could happen is an error message, is probably a lot better than if you spent all this time building a prototype. The way we're going to build this robot model is from within MATLAB with simple shapes, which is why the robot looks the way it does. With Simscape Multibody, you can build 3D models, and most importantly, you can parameterize them using MATLAB variables. For example, you see on this slide, for a particular link in your robot, you could link this to MATLAB variables like the density of the part, the radius of, if this part is a cylinder, as well as the length of that cylinder. And you can further associate all these parameters with some kind of MATLAB file that is customizable and linked to your model when it opens up. So I'm going to type in the command smnew, which will create a new Simscape multibody model. And you'll see that it already contains a couple of initial blocks, like the solid block or the rigid transform block, which are key blocks to building any model with this tool. So we'll start by developing our system. Instead of solid, I'm going to rename this to leg, and we'll set up the geometry of the solid. So again, this is a cylinder, and we can give it a particular radius, length, and say inertial properties. For example, the density. Now, as I said before, we don't want these to be just hard-coded variables, so I'm actually going to open up and run a file that I've already created that contains all our robot parameters, and these are stored in a MATLAB script. So for example, let's go down into the leg parameters, and you see here I have variables such as leg radius, lower leg length, and so on. So let me run this script, and you see that that will populate my MATLAB workspace on the right with all those variables that I've just created. So now I should have access to all of these from my model. All right, so let's say that this is a cylinder, and our radius then is going to be leg radius, and I'll set up the units as well to centimeters. A length of lower leg length, also in centimeters. And I've actually also loaded a parameter for the density. So we'll create all of those, refresh our view, and you see that this is the cylinder representing the leg of the robot. Let me give that a different color real quick. Just make that blue. And that's our shape. Of course, now we need to define all the coordinate systems in motion around that shape. I'm going to use the rigid transform block to define coordinate systems in relation to that leg. So the frame that gets created here is at the center of the cylinder. So I'm going to create two coordinate frames on either end of the cylinder. Let me actually create two of them. So we'll create, the bottom end and the top end. For the top end, let's do a translation about the z-axis, which is the length of the cylinder, and that's going to be the 1/2 of the leg length. So in other words, half the length of the cylinder in one direction in the z-axis. And I'll also create a rotation just to align my axes to make it easy to add rotational degrees of freedom. So here I'll do a rotation about the x-axis in 90 degrees. Actually, for the other one, it's a very similar translation where I can do, again, in this case, I'm going to do a minus z with the same leg length divided by 2 in centimeters and give it a similar rotation. Oops, my standard axis. And then we'll shortly see what this looks like. So let me just connect this to the world frame and start by updating my model. And you'll notice that if I click in the Mechanics Explorer on the left, I see that the cylinder itself has its coordinate frame at its center, and then the two rigid transform blocks create new coordinate frames at the bottom and the top of the cylinder. Now we still have to add degrees of freedom to all of this. So let me go back here and bring in a revolute joint block. Set it up there, and I'm actually going to add another rigid transform block just to continue rotating things such that it makes sense. And this one will just have a rotation, and you'll see what that does in a second. So the last thing we can do is set up initial conditions for this joint. So we'll say in the position target, I'll set the initial angle to 30 degrees. And let's see how that changes now if I try to run the simulation. Indeed, you see that this now moves like a pendulum. And I can slow that down so it's a bit easier to see. So again, this is just basics of how you build the model. The most important thing is that now you're able to associate multiple blocks with the same parameters. For example, the solid block representing the leg, as well as the two rigid transforms around it, all the three of them reference that leg length parameter. And if we change that length in the MATLAB command prompt, if I say lower leg length is, 15 instead of 20, I can go back to my model and resimulate it now with a longer length. It should all work out accordingly. So let me reset that to 10. Now, the other important thing to note is whenever you create a model, it's good to have all this data loaded as you load the model. So I'm going to go to the model properties here by going to File, Model Properties, Model Properties. And in the callback section, I'm going to add to the preload function callback a call to our script, robot parameters. So this way, when I start up the model, all that data should be loaded for us. And let me save that model. Let's talk about defining the motion of the joints now. Again, all that we did so far is create the initial condition for that pendulum link representing the leg, and then we just let it simulate under the effects of gravity. Now, if we're going to create a walking robot, we're actually going to have, actuated joints. And the way we're going to do this, for starters, is by supplying a motion input to the joints. So we can configure the revolute joint block to accept a Simulink signal representing that angular motion. And as we start building this model, we'll see basically what kind of walking trajectories we can input into our ankles, knees, and hips. The way that you prescribe motion in Simscape Multibody, you don't want to provide discontinuous derivatives into the motion. So you can imagine, for example, if you have a signal that's like a step response or a staircase, that means that you're going to have infinite derivatives, in other words, infinite velocity and acceleration, which means infinite torque, and that the solver doesn't particularly like that. So it's always good to filter these signals with some kind of time constant to provide a smooth motion profile. If you look at the figure on the right, you'll see, for example, for a particular trajectory, which is in the blue, just a completely unfiltered signal, which is just a bunch of waypoints with linear interpolation in between. As we start adding filtering to the signal, we can smooth it out at the expense of adding a time delay. So you see the red signal has a large time constant, which makes it smooth, but it's pretty far away from the original curve. And as you bring the time constant to a smaller value, like in the black line, it's a bit less smooth, but closer to that original set of points that we prescribed. You want to select a time constant that is small enough to not impact the overall dynamics of the system. So it should be faster than most of the other things happening in your model. But at the same time, you don't want to make it too small because that's when you start getting, very sharp changes in the derivatives that you're inputting into the system. Right, so if we go to the revolute joint block, I'm going to set up under the actuation, going to say that the motion is provided by input and that the torque that makes that motion happen will be computed automatically. Furthermore, I will be measuring the actuator torque. So let's apply that, and now you'll see that the revolute joint has been given input and output ports for the motion and the torque, respectively. So let's take the easy part first. Let's grab the converter block and the scope that was given to us and measure our actuator torque in units of Newton meters. And we'll label this signal. And then for the input, we'll do that. And then we need to figure out a Simulink signal to supply. So in this case, I'm going to use a sine wave function, like so. And I will supply it some amplitude and frequency just to test things out. So here I'll use 46 and 2. So 46 degrees of amplitude and 2 radians per second of frequency. And again, to make sure that our units make sense, we should go into this converter block and set our input signal units to degrees. Otherwise, we'd be doing a 46 radian input, which is not cool. The filtering that I was talking about with actuation will be under the input handling tab. And this is where, I can modify this and either provide a first or a second order filter. So I'll do a second order filter with a time constant, again, provided by my parameter file, motion time constant. And I think that ended up being 0.01. Okay, so we'll do that. And let's run the model and see what happens. So again, if we look at the Mechanics Explorer, let me take that up to full speed. This is going to be our motion now. So you see that it's following that sinusoidal trajectory for the motion of the leg. If I go back to the model, I can go into the scope and visualize the torque that was needed to make that happen. And you'll see that the values of this torque are fairly small. They're about 6 times 10 to the minus 3 Newton meters in amplitude. And this is mainly because we haven't added any internal mechanics to the joint. In other words, if I go back to the revolute joint block, you'll see that under internal mechanics, my stiffness and damping coefficients are 0. So it doesn't take very much acceleration to get these things to move. So now if I were to change the spring stiffness, I believe I have parameters for that, but I'll just pick something for now. If I pick 1 Newton meter per radian as my stiffness, let's say, and let's do a damping coefficient as well. Let's make it something fairly small. If we change these parameters and try simulating again, we should get the same motion, but with different torque requirements. Now you see that the required torque is closer to something like 3/4 of a Newton meter. So this is how you can get started simulating or creating the model of the robot walker. So you can imagine that if you follow the same strategy, you can start building up the whole system. If I go to my intermediate subfolder here, you'll see I'll find my first file, which is walking robot step 1. And I'll just open that up. This again takes the same approach that we modeled, but if you look into the robot subsystem, the left and the right legs have been created fully. So it's the same thing, right? You've got your revolute joints, your rigid transform blocks, and your solid blocks. And right now there is no input to any of these, right? This is just starting naturally from some initial conditions. So if I simulate this model, you'll see this is what it looks like. So I have my robot pinned by the body. So you see that the torso is not moving, and then the legs are just swinging like a triple pendulum in this case. And then if we add actuation, it will look like the second step. In this case, if I click inside the robot subsystem, you'll notice now that there's a new level of hierarchy, and what we're doing here is we're prescribing the ankle, knee, and hip motions by creating variables. So you see, for example, if I go to the ankle motion block, this is just a repeating table of time versus the ankle motion. And I can show you what that looks like if I go into MATLAB. So let me clear this. You'll notice that I can just do plot of time, comma, ankle motion, and let me actually convert it from radians to degrees, just so we can view this in a more intuitive way. And let's also use markers so that we can see the actual waypoints of the ankle motion. You see, this is what it looks like. It's just some trajectory of points that goes between 0 and 0.8 seconds and then repeats this sequence. And of course, remember that these things are going to be filtered so that the trajectory is going to be smoother than this. So the other thing that you'll see here is that there's a transport delay block, and this block adds a delay of 1/2 of the period of our gait to the left leg. In other words, it's saying that the left leg is going to be lagging our right leg. And then you see that in the right and left leg subsystems, they're identical to each other. I'm taking the input signals for the ankle, knee, and hip joints, and I'm prescribing them to the revolute joints, as you see there. So if I run this, now you'll see that we have something that looks sort of like a natural walking gait. Let's zoom in there. But the robot is still fixed by its torso and it's not walking. And that's because we're missing a key element of simulation. And that is the actual contact between the foot and the ground. What I'm going to do is select contact points at each of the four corners of that foot. And at each of those four corners, then I will create a contact between that point and the ground. To do that, I'm going to use a library that's available online on the file exchange called the Simscape Multibody Contact Forces library. If you've been following the MATLAB and Simulink robotics arena, you'll see that we have a couple of videos about contact forces. So if you're interested in this, feel free to check it out. What I'm going to be doing is for each corner of the foot, I will use the sphere to plane force blocks to model that contact. Okay, so I will open up the Walking Robot Step 3 model, and we'll observe the differences here between this and the previous model. The first main difference is that now there is a 6 degree of freedom joint between the world and the robot. And this 6 degree of freedom joint is what allows the entire robot to move freely in the world. And what's going to keep it constrained to the ground are going to be these contact blocks that we've added into the robot subsystem. So let's dig in here. Going into the leg subsystem, now you'll see that there's a lot more going on in here. So let's focus on the foot solid block. You notice that compared to the previous example, this contains a lot more coordinate frames that are coming out of this block. And the way that this was done is, again, by going into the solid block, we actually have a frames menu where we can create coordinate frames that create ports in this block. So for example, you see that there are 4 coordinate frames called F1 to F4, which correspond to the 4 contact points at the corners of the foot. And then there's a 5th coordinate frame called A, which denotes the ankle connection. So let's look into F1 just for a second. The way that this has been selected is by actually clicking on one of the corners of this brick. And then on the left, you see that there is an option for the frame origin called based on geometric feature. So what I can do is I can click that corner point and then hit that use selected feature button, and that will create a coordinate frame at that point. And you can do the same thing for things like faces or edges of shapes, as well as certain features in parts that you might have imported from CAD. So now that we have these 4 frames, F1 through F4, for the corners of the foot, then I can add in that sphere to plane force block, where I just have a tiny sphere in contact with the ground plane. And then really the other additions to this model are all about measurements. So it's just a way for me to grab a lot of interesting signals that I might want to double check and then pull them out to the top of the model where I have logged them. So that's why you see the little logging icon on those signals. Okay. So what I'll do is I'll run this simulation, and now you'll see that compared to the previous simulation, this robot is walking under that prescribed motion that we gave it. Now it can be tricky to fit the contact parameters to make sure that the walking is accurate. So one of the key things to do, or that you might want to do, is take a look at the way the contact forces work for the the walking trajectory that you're giving your robot, and check if that agrees with any data that you can collect. Because typically when you get walking data from your robot, you will see kind of the magnitude and the duration of those contact spikes in force. So if you're able to find parameters that can agree with that, that'll make sure that your simulation is close enough to reality so that it's useful for you. So now that we have logged data, you see that our simulation data inspector icon is glowing, which means that we have data that we can visualize. Let's open that up, and you see that I have my run from simulation logged here. So I can plot different things. For example, in the first subplot here, I'm going to show the ankle angle, the knee angle, and the hip angle. And I'll just put those all side by side with different colors. So you see that right now most of my signals are sticking to about 15-ish degrees of motion. So it's a pretty gentle walking gait. I can also look at the actuator torques that went into this. So for the second plot, I'll select the ankle torque, the knee torque, and the hip torque for the right leg. And again, here you see that the biggest torques are somewhere around 5 Newton meters, and that's going to be the hip. So you can use this information to verify whether, to meet this motion profile with the mechanical parameters of the robot, are your actuators going to be able to produce this amount of torque at that velocity? And then at the bottom here, I'm going to log some of the contact forces. So what I'll do here is I'll show you the normal and the friction force for the right leg, and you see that they're in some way related to each other because the friction is partly proportional to the normal force. Maybe let's uncheck the normal force. So I'll show the friction force between the left and the right leg. And then if I start zooming in on the time axis, you'll notice that, comparing the yellow and the pink lines, which are the right and the left legs, that they should be completely out of phase with each other because of how we set up the walking gait. And that also holds true for, the torques and the angles. What about next steps on the mechanical modeling side? There's a couple of things I wanted to discuss before we end here. The first thing is that instead of modeling the robot directly with MATLAB variables, you can also import your design from CAD software. And one of the ways that we've allowed you to test this is by providing an Onshape model online. And that link will be in the description. There are also a couple of models in the file exchange submission for these videos where it will automatically, download that Onshape model and import into Simscape Multibody. So what this ultimately means is that there's another workflow besides modeling and managing all the parameters in MATLAB. You can also do the same in your CAD software and then import into Simscape Multibody and start adding in things like the contact forces and the actuation and the control within these tools. So I invite you to try this out with your own CAD model if you're building a walk-in robot. In addition, and we'll do this in the next video, we'll talk about modeling more realistic actuators. So right now, we're just prescribing the motion of the joints. However, you might also be working on actuator control. So how can we, instead of just telling the joint to move to a particular location, can we actually create a closed loop controller that tries to manage that angle of the actuator? And in addition, the actuator is not just, you don't just prescribe the torque. You might have some kind of other actuator like a motor or a pneumatic actuator or a hydraulic actuator. So can we use Simscape to model these multi-domain systems and link them into our 3D model? And then in the final video, we'll be looking at learning to walk. And there are a couple of techniques here. The first one is optimization, which is essentially learning, some open loop strategy, or in our case, a walking gait that is stable and meets our requirements. But you can also keep going with this and, start using things like machine learning or deep learning to create a walking policy that is learned by trial and error. So if you're working on this, I'd be really interested to know how you're going about it. So hopefully this gives you a brief introduction to modeling the mechanical portion of a walk-in robot using Simscape Multibody. As always, feel free to contact us via email or Facebook, and check out the other resources below. Thank you for watching.